Okay, today in vectors, it's actually the fourth day of vectors, so it's called day 4. We're going to be doing a lot more with 3D vectors. So first of all, I want you to understand a simple vector, 2i plus 3j. There's 3 directions, I, j, and k. What do you mean 3 directions? There's only an x and a y. In the past, yes, there's only been an x and a y. And now we would, in vector world, call those I and j. But there's also k. K comes, imagine, I can't really do this for the video's sake, but imagine this is coming out towards us, making it dotted because it's like imaginary. It's coming out towards us. It's that third axis. All right, so I have something in the room here I'm going to use to demo, so I'm going to pause for a second. I'll set that up. So if I originally only had 2 dimensions, and now in the room I've got this 3-dimensional kind of thing set up. That black vector, this guy right here, 2i plus 3j, aka 2, 3. Remember that from before? Okay. Do you get that would have to stay in this plane here? Because we didn't have a plane that went towards you. We didn't have that direction before. We just had I, this is I, that's j, and then this one's k. The k is the one that comes out right towards you, okay? All right. So, this is my 2, 3. Okay, over 2, up 3. There. Now, what if I made it 2, 3, 1? And I just kind of extend this out a little bit further. And that would be plus 1k. Oops, that's made it I. Don't want to do that. 1k. Positive is towards you. Negative is away from you. I don't want you to envision what that would look like. Okay, over 2, up 3. Do you get that I'm doing that right now? And then 1 would mean it tilts towards you 1. This vector right here, that's going over 2, up 3, and then goes out towards you 1, is like that. Okay. Now you remember from yesterday that if you add vectors, it was as simple as, let's say this vector. You just add the top numbers, you add the bottom numbers, all there is to it. Remember that? All right. I want you to picture, though, what that actually looked like. Would you draw for me what 2, 3 looked like? And would you draw for me what 1, 4 looks like? Make them different colors. You have that capability on your iPad. Draw 2, 3, draw 1, 4, and then actually put them together where you go tip to tail. And you know the answer should be 3, 7. And let's see if it actually comes out at 3, 7. It will if you do it right. 2, 3 plus 1, 4. I'm just asking you to make the pictures for that. 3-dimensional pictures are much more of a pain, and that's what you're going to do in a minute. But I'm going to pause while I get that a nice graph up. Okay, I'm drawing my 2, 3 vector. Goes over 2 and up 3. I'm putting a dot, and then I'm making that little vector. Just to clarify, is that the magnitude? 2 and 3, are those the magnitude? No. That's this distance of 2, this distance of 3. And so the magnitude is the length of that little blue vector. Have you got this vector drawn? On, like, somewhat to scale. Got to keep up with me here, otherwise you will get completely lost later. Now, draw the vector 1, 4. It goes over 1 and up 4. There's the vector 1, 4. I made a curve. I don't want it to curve. I'm making it straight. Curved again. Close enough. And I suggested you show how you add them. You go tip to tail like this. Boom. And look at that. It goes to 3, 7. Just like we predicted. Top would be 2 plus 1 is 3. And bottom 4, 2, 7, 3, 7 is the new vector. You can imagine that the same exact system will work at 3D. It's just tougher to visualize. So if we had to do 2, 3, 1 plus 1, 4, 5, those would be three-dimensional vectors I'm going to try to do on a board like this. I could do it in the room, but, and then it puts, this last one would be a 6. You just, if you're going to add them, you simply add them. Did you remember that yesterday you could throw a number out front and scale it up? Would you please tell me what vector you would get if you times 2 times the 2, 3, 1 vector, and then added the 1, 4, 5 vector, just to make sure you get how to do this? The answer is 3 simple little numbers in a column. It'll stack. Let me pause for a second while you find those 3 answers for me. Okay. Did you get 5, 10, 7? Raise your hand if you got that. Okay, good. And you kind of caught up. Now, what we're going to be doing is 3D vectors. So let's find a slide that's got a nice example. Here we go. And it really does help that they've drawn a box, because you can picture this as like sort of like a clear box. And it does say the length of each edge is 5. That means if this is really a cube, that's 5, and that's 5, and this is 5, and this is 5, and this line's 5, and this line's 5, and this is 5, this is 5. I think you get the idea. So if you wanted to get OG, it's like Jeopardy. They're giving you the answer. The answer to this question is OG. And the question is, what could you have done to get there? Now, there is actually a bajillion ways you could get there. Think of it as you could only walk on these, and they're like wires, like high wires. And you could only get to this spot here. That's your goal, is to get there. B, by walking on the wires. Do you get that you could go OA as a first step, but there's actually like a million options? On my next step, I could go from here to here. And then my next step, I could go from there to there. Apple, apple, sat. That'll work. Okay. And then how do I describe that? Well, this move was from O to A, and it was, you'd have to go 5 and the what direction? Well, they got them labeled here, so you can look close. You see they call that the I direction. Okay. And they have, this is like, it's almost like they took the graph and laid it down. So the K is coming up. This is the K direction. It's like, think of this as your XY graph normally. You know, like this is laying down here. Here, I'm going to undo all the writing I just did. Okay. Here. And I'm going to say this is like the X and the Y axes. And then they have K coming up. They could have made K be the one that was coming out towards you more, but this is the way they chose to do their I, J, and K. So their I is here. This is the I axis. This is the J axis, that one. And then this is the K axis going up. All right, so if I was going to say OG, to get to OG, that's this guy, I'd have to go, for instance, O to A, and that's along the I axis, and so you'd say 5I. You have to go 5 in the I direction. Plus, you'd have to go 5, of course. They're all blocks of 5, right? All right, I think you've got the idea here. And you're supposed to write me a little problem that will make it, the answer be OG. Okay. So I've got the answers here. I'll reveal them in a minute, but I want you to work on this. I'm going to give you a partner and give you a little bit of time. Let's see if you figured this out. 5I 5j, and 5k. Now, do you get that you could have gone in any order that you would have wanted? Like if you're really walking to this place, yeah, or climbing, so to speak, go up. It didn't really matter. But when we write them, we always put the I first. So you could have just written it any way you wanted, but then rearranged it, put the I first, then the J, and then the K. Raise your hand if you figured out all three of them. All right, good. Okay, so let's move on. I think you got the idea of the whole the 3D vector idea. So how are we going to do this one? The vectors u and v are given by this. Oh, well, first of all, right away, I like to write it this way. 3, 5, and 1, negative 2. Do you get I just changed that into blank form? What form is that? Column form. All right. Now, it wants me to take A times u plus v. Well, what is u plus v? Well, it's just these two added. And have it equal 8i plus b, which is what again? They don't tell me. Something I don't know. Minus 2 times j. What in the heck are they talking about there? These are really like deep thinking questions. Okay, so this is where we're kind of headed. Don't expect you to be like, obviously all you have to do is this. Okay, but u plus v, I hope you could have figured out, was these two added together. And then it's got kind of a, well, it's got it written in this IJ format. Do you get that really means that I could be writing this as a column vector? Hint. Write this as a column vector. And see if you can figure out what to do to solve it. I'm going to pause for a second while you do. This is not easy, I know. Take one little step at a time. So once you got it rewritten like this, do you get that you get two little equations that kind of fall out? If these are really equal, then 4a has to equal 8. Does that make sense to you? And then 3a has to equal b minus 2. 4a equals 8 for the top row. On the bottom, 3a equals b minus 2. Well, that'd be great if I knew what a was, but I do know what a is because of that. What's a got to be? A's got to be 2. So then you can put a 2 here, and then it really wasn't that bad, was it? Okay, so this type of a question makes you think about what vectors really mean and how you can make them into equations. All right, you're going to see one of those on your homework for tonight. All right, let's say that we were doing one of the problems from yesterday. I hope right away you see this and think 1, 7, negative 1. All right, when it did 3 times, oh wait, it was 3 times b. So here's the b one. The b1 was 4, 7, 5. When they wanted 3b, they wanted 3 times, what was b again? 4, 7, 5. So you just multiply it out. 12, 21, 50. Okay, so that's what you've done before. So now let's look at what's new. The magnitude of a vector. This makes it look like it's a really complicated process to figure out the magnitude of a vector, but it's really not that bad. If I just said I had the vector 2, 5, would you draw it for me real quick? Draw 2, 5. I think this will really help you understand it. Going back and forth between the pictures and the equations is kind of critical. So remember, what does that look like? We go over 2 and you go up 5, and did you draw a line that kind of looked like that? If you were going to get that magnitude, as in how long that red line is, do you get it depends on how far over you went and how far up you went? And so really this one is just the square root of this squared plus this squared, because it's the sides of a triangle. And it's 2 by 5 And so it's 2 squared and 5 squared, or 2 squared plus 5 squared, and then that would be 4 plus 9 is 13, square root of 13. Raise your hand if you got square root of 13. Well, then all you were doing was this formula right here. You took the square root of this one squared plus that one squared. Did I screw up my adding there? I was doing 5 squared is 10. 25 plus 4, 29, square root of 29. My bad. All right. Okay, so back to what you were really doing then. There's a lot of talking going on right now. That shouldn't happen because this is getting complicated and you'll get lost while you're chatting away. All right, that squared and that squared. That's what we just did seconds ago. That was pretty easy. But did you know that there's something like that for 3D? You just throw in the third one squared also. Now, could you draw it every time and then figure out the triangles that go with that and stuff? You could, but it'd be a lot easier to just extend it and say, well, you always just took this side squared and this side squared, and then took the square root of that. You just do that for the third dimension also. All right, so if you were asked to find the magnitude, as in how long this little vector was, I'm going to show you in the room what negative 2, okay, so I'm going to try to do this in feet, okay, and I'm going to say negative 2 feet. At first, that's the x direction, so that's 2 feet over this way. Ready? I'm going to follow the pointer finger here. I'm going 2 to the left. That's about 2 feet, isn't it? Okay, and then what's the 3? That means I got to go up 3 feet. Now I need something to point with this longer here. Grab this. Okay, so I'm going 2 to the left, up 3 pretty much puts it right on the ceiling, right? Is that about 3 feet? Okay, so over 2, up 3, and then what's that last negative 1 do? Does that go towards you or away from you? Away from you about a foot. So I'm going to go from here to away from you about a foot. It's right there. So the vector is from my hand to that spot. That's the vector. How do I get its length? A squared plus b squared equals c squared. But in this case, it's a squared plus b squared plus c squared equals d squared. It would work. All right, and it would take me probably 15 extra minutes to show you. I'm not going to show you, but we're going to do this one. Square root of a squared plus b squared plus c squared, or x squared plus y squared plus z squared. But anyway, there's your 3, and everybody figure it out once. We should do that. And why do they have absolute values around this thing? Because it's saying that's what the magnitude is. We don't even care what the direction is right this second. We're just figuring out how long that line would be, how long that vector would be. Without further ado, square them all up, add them, and see what you get. I'm going to pause for a second. Wait. So then you got 2 squared is 4, 3 squared is 9, 4, 9, and 1, square root of 14. Whoa, hello. Who's got that one right? Raise your hand if you had that one right. Okay, good. Remember, that was the magnitude of it, how long the vector line was. Now that could be, it depends on what you were measuring. It could be in speed. A lot of times we use speed. A lot of times we use, that this is a number of feet or whatever. It could be a distance. It could be a speed. It could be even a power. Remember that example of the robot pulling on the rope and you're pulling on the rope? And both of those are measured in, well, they could measure it in newtons. They could measure it in feet per, like foot-pounds of how much power is on that. Could be horsepower. Oh, so many things. Anyway, the magnitude is just a number, though. And that's why it has the bars around it, because we don't care what the direction is. Absolute value is, it's kind of like absolute value. All right. So let's get to the next slide. This. A unit vector. By now, have you figured out what unit means? We had the unit circle, right? What did the word unit mean? 1. Okay. So a unit vector would be like, okay, remember that last vector we just had, and I'm demonstrating it in the room here again? It was kind of like that. Remember that one? That one had a length of like, I don't know, I'm just looking at it saying it's probably about 3.5 feet or so. A unit vector would be a vector that's going in the same exact direction as that, but have a length of what? 1. All right, so how do we make a unit vector? And by the way, the little symbol for that is this little hat. A hat. All right, so if I want a unit vector, something that's only a 1 and heading in that direction, it's really, really handy. Let me explain why before I even tell you how to figure it out, why they're really, really handy. If I have a unit vector that's exactly, let's say we're going with feet, okay? And let's say it's exactly, I'll find my one that's exactly a foot long here. There we go. All right. This unit vector that's exactly 1 foot long, okay? If that's heading in a certain direction, and I want to scale it up and say, oh, by the way, I want the vector to be 43 feet long in that same direction. Remember our original one we figured out earlier? This guy, that I figured is about 3.5 feet long, okay? If I wanted to scale it up and say, I want a vector like that, except I want it to be 53 feet long. The first thing you do is say, okay, well, let's scale this back to be just a unit vector in that same direction. And that says, okay, same direction and only 1 foot long. Boop, now it's like this. It's easy to do. I'll show you the little formula for it. Now you'll have this little 1 foot long vector in that direction. And then if I want it to be 53 feet long, I take the unit vector and times it by 53. See what I mean? So if I have a vector, let's take a new one now, okay? I know that this one is exactly 4 foot 11, and therefore 5 foot would have been 60 inches. So this is 59 inches long, okay? If I have this vector that I am now demonstrating in the class, 59 inches long, and I reduced it down to just a unit vector in that same direction, it'd be 1 inch long instead of 59 inches long. And all of a sudden, I got this little 1 inch long vector going that direction. Now, if I say, I want it to be 1,000 in that same direction, 1,000 inches long, I take my unit vector times by 1,000. Okay, so that's why unit vectors are really, really powerful. And they'll be able to answer an R3 question for you really easily. This should be an easy one, if you just learn how to do this little trick. Okay, so it says A over absolute value of A. Let's try to figure out what that means. I'm trying to find a vector in the same direction as my original one, except I want it to shrink down to be the length of 1 instead of like, here, this one's 59 inches long. I want it to be smaller than that. I want it to be 1/59th as long, so that it'll be exactly 1 inch long. I'm going to give you the task to try to figure this out. We'll use a real vector here. We'll say our vector is, actually, let's use a nice Pythagorean triple. Except it's not a Pythagorean triple anymore. You know what it is? Pythagorean quad. That means I have to figure out one where I know a nice, easy length that's based on going out like 1 over 1 up. Who can think of one that would work nice? Pythagorean triple, so that you can give me a vector where the 3 numbers would work out really nice and would give me a nice square root. And your goal, right this second, find any triple combo where when you do their square root, it works out perfectly. Pause for a second for you. Well, you figure out one that would have a really nice magnitude. I don't want the magnitude to be like square root of 14. I want the magnitude to come out nice. Use simple numbers like 1s, 2s, 3s. I'll pause for a second while you figure out a nice combo. By now, somebody nice must have figured out a Pythagorean triple that actually would work with 4 numbers. In other words, these 3 numbers, a squared plus b squared plus c squared equals d squared. Give me a 3-number combo that worked. Oh, seriously, nobody? What'd you get? All right, 9. Oh, sorry. 9, 2, and 6. I'm going to check it for you. That means if you're right, the magnitude of this works out nice, so it must be a nice number underneath the square root. 9 squared is 81. 2 squared is 4. And 6 squared is 36. 40 and 81 makes, what is it, 121? All right, very nice. So square root of 121, which was 11. Okay, all I was asking is I wanted one that would make a nice clean number. All right, so 926, that one has a length of 11. It's 9 in the one direction, 2 in the other direction, and 6 in the other direction, and you end up with an 11-inch or 11-foot long. All right, now, sorry, trying to avoid the loud teenagers. You could go and yell at them, but I don't think it would help. So, all right, so I'm going to say I've got this one that's 11. Don't overthink this now. How do I scale that down to be a unit vector? If it's 11 long right now, I'd have to multiply it by what to shrink it down to be a length of 1. I'd take my vector here, and I'd have to multiply it by something to make it shrink. 1 over 11. Because it's 11 long right now, right? And if I multiply by 1/11th, that'll make it shrink down to be 1 foot long, or 1 inch long, or whatever our units are. See what's happened there? I had to figure out the magnitude, which is this thing. And once I had the magnitude, I had to do 1 over the magnitude. I don't like the way this formula looks. Here's how I would write it. 1 over the magnitude times the original. Now that does come out to A over absolute value of A. It's not the absolute value, it's magnitude. Okay. So if I give you another one, even if it doesn't work out nice, even if it doesn't come out to the square root of 121 that worked out so nicely, let's say it comes out to the square root of 7, you should still be able to do it. So I'm going to give you one right now. 1, 2, and 3. That's your vector. It goes 1 to the right, 2 up, and then 3 out towards you. That's my vector. Its length is not a super, well, I'll let you figure out what its length is. Then you figure out how to make it into its unit vector. You just got to multiply by something in the front. I'm going to pause for a second. Let me try that. Okay, I'm going to call this vector Q, so I put a Q above it. And what is the bars around the Q stand for again? Magnitude. What's the magnitude of this puppy? Square root of 1 squared, 2 squared, and 3 squared. So that's 9, 4, and 1. 9 and 5, 14. Did you get square root of 14? Yes? I hope. Okay, good. Then 1 over the square root of 14 times that. What did it do? It just shrunk it, right? Because I multiplied by 1 over this, I multiplied by a fraction. I shrunk it down, and to what size? How long will it be now? It'll be 1. That's the concept of finding a unit vector. And what does that allow you to do? That says, let's say you've made this cool little model, and it's like artwork, okay? In our case, it's just going to be really simple. It's just a vector, and it's small. It's like this. And you were like, oh, that thing is so cool. Maybe it's like a dolphin or something, and it looks really cool. And it happens, I'm simplifying it down to just a vector. And then they say, you know what? I want one like that. but I want it to be 15 feet long. And we'll put it out in the front lawn of the school. Okay? All right, so here's the vector that we start with. -1, 2, and 5. That's the vector we had in the first place. I want that vector, except it currently is not 15 feet long. I want it to be 15 feet long in the same direction. I'll pause for a second while you figure that one out. Hint, you want to use a unit vector that we just figured out how to do. And then there's only one tiny little tweak to it and you're done. I'll pause while you try that. The first thing you needed to know, I'm going to call this R, would be the magnitude of R. So you should have figured that out by doing square root of a squared plus b squared plus c squared, or I squared plus j squared plus k squared. And so 1 squared is 1, plus 2 squared is 4, plus 5 squared is 25. Square root of 30. Then, once I have that, I'm going to do 1 over that. And that is a vector in the direction that we wanted, and it's only a length of 1. And then it's not that complicated. If you want it to be 15 feet long, I now times by 15. And do you think if I times by 15 in front, it would be just as good as timesing by 15 right here? It'd do the same thing, wouldn't it? We usually do it that way just so it isn't 3 fractions being multiplied, you know. And then the final answer is 15 over square root of 30 times -1, 2, 5. Now, if they actually wanted you to multiply it all the way out, it wouldn't be that hard. I just have to multiply this by each of them. Final answer, 15 over root 30 except negative. And then multiplying this times this would be 30 over root 30. And last but not least, we'd have 15 times 5 is 75 over root 30. All it is me just kind of distributing this in. Here, here, and then there. Okay. There, you learned another cool thing you can do with vectors. Basically sizing them. First you size them down to be length 1. And then you can upsize them to any size you want. Super easy. Okay. This should be easy for you right now. I don't want to give you any descriptions. I just want you to try to answer these 4 questions. I'll pause for a second while you give it a shot. Okay, by now, if you don't know what these things mean, I should tell you. I hope you did. This is find the magnitude. This is find the unit vector. And then using that unit vector, you answer these 2. All right, just making sure you have something to do in case you didn't know what those little things meant. Magnitude, unit vector, and then use the unit vector to answer the other. Okay. So this would have been 1, 2, -1. And to find its magnitude, it would have been square root of 1 squared, 2 squared, and 1 squared. What did you get on this one? Square root of 6. All right. And then the little hat, that's 1 over the square root of 6 because we're trying to take its length and 1 over its length and then timesing it by this. That will shrink this down to have a size of exactly 1. That's the unit vector. It's still the same direction. It's just that this thing shrinks it down so it has a length of 1. So then if you times that by 5, it'll become 5 units long. So if I times this by 5, I'm just going to times by 5 right here in front, which will jump up to the top because it's really 5 over 1, right? So then it becomes 5 over root 6 times 1, 2, -1. And you could, of course, multiply that out to each little piece if you wanted to. Same thing for the 100, except it would be a 100 right here. All right, cool. Now, let's talk about a scalar product, also known as a dot product. Sadly, I know we're leaving very soon, but this is one more thing I have to teach you, but it's really, really simple. If I have 2 vectors, 1, 2, 3, and another vector, 4, 0, 3, the dot product, you would put you would write the word dot. Otherwise, you will think we are multiplying these vectors. Okay, the dot product of this is really simple. 4 times 1 plus 2 times 0 plus 3 times 3. And that gives you 4 plus 2 times 0 is 0 plus 9 is 13 is the dot product. All right. You are going to do the first 2 pages of the homework that is in this section. The first 2 pages. And we will clean this up tomorrow and make sure you're experts at dot product and then what that means. Have a good day.